The next step after differentiating vectors is to integrate them. In this session, we will start with line integrals and proceed to surface and volume integrals. Line integrals. Let us consider a path starting from a point A to end at point B as shown in this figure. Let us also consider a vector function v along this path. If the path is divided into infinitesimal sections having length dl, which is given by dl equal to dx times x hat plus dy times y hat plus dz times z hat, then a line integral is an expression of the form integral a to b v dot dl. If the path is closed, then it is indicated by putting a circle on the integral sign as integral v dot dl. At each point on the path, we will take the dot product of v evaluated at that point with the displacement dl to the next point on the path. The most familiar example of a line integral to a physicist is the work done by a force F. This is given by W equal to integral F dot dl. Ordinarily, the value of a line integral depends critically on the path taken from A to B. But there is an important special class of vector functions for which the line integral is independent of path and is determined entirely by the end points. A force that has this property is called conservative. Let's now try to calculate the line integral of the function v equal to x square x hat plus 2yz y hat plus y square z from the origin to the point 1, 1, 1 by the three different routes. Route A starts from 0, 0, 0, goes to 1, 0, 0, then to 1, 1, 0 to 1, 1, 1. And route B starts from 0, 0, 0, 0, 0, 1 and then it goes to 0, 1, 1 and then goes to 1, 1, 1. And the third route is a straight line connecting 0, 0, 0 and 1, 1, 1. We also are directed to calculate the line integral around the closed loop that goes out along path A and back along path B. Let's now try to solve the part A of the problem. Let us try to calculate the value of the path integral in going from 0, 0, 0 to 1, 0, 0 first. In going from 0, 0, 0 to 1, 0, 0, the value of x varies from 0 to 1 and value of y and value of z is equal to 0. We have dl as equal to dx x hat plus dy y hat plus dz z hat. Since dy and dz are equal to 0, this will be equal to dx times x hat. There is variation only along the x direction. Now when we calculate the line integral v dot dl, this will be equal to integral x square x hat plus 2yz y hat plus y square z hat dot dx x hat. So this is equal to integral 0 to 1 x square dx, which is equal to x cube divided by 3 from 0 to 1, and this is equal to 2 by 3. Now Let's calculate the value of the line integral in going from 100 to 110. In this case, x is equal to 1, value of y changes from 0 to 1 and value of z is equal to 0, which gives us dl as equal to dy times y hat. Therefore, line integral v dot dl is equal to integral 0 to 1 to yz dy, which is equal to 0. We'll now calculate the line integral in going from 110 to 111. In this case, x is equal to 1, y is equal to 1 and value of z changes from 0 to 1. In this case, dl is equal to dz times z hat, and the line integral v dot dl is equal to integral 0 to 1 y square dz, that is equal to integral 0 to 1 dz, that is z with limits 0 to 1, which is equal to 1. And the total of the line integral will be equal to 1 by 3, which is the value of the line integral in going from 000 to 100 plus 0, which is the value of the line integral in going from 100 to 110 plus 1, which is the value of the line integral in going from 110 to 111. Hence, the total value of the line integral is 4 over 3. Part B is to calculate the line integral in going through a different route. It starts from 000, goes to 001 and then to 011 and finally to 111. So we'll split the entire route into 3, from 000 to 001, from 001 to 011 and from 011 to 111. In going from 000 to 001, we know that x is equal to 0, y is equal to 0 and the value of z changes from 0 to 1. From this, we can write dl as equal to dz z hat. Therefore, integral v dot dl is equal to integral y square dz, and since y equal to 0, this is equal to 0. In going from 001 to 011, we have x equal to 0, y changes from 0 to 1 and z equal to 1. Hence, in this case, dl will be equal to dy times y hat. Therefore, line integral v dot dl will be equal to integral 0 to 1 to yz dy. So this is equal to integral 0 to 1 2y times dy, which is equal to 2y square divided by 2 from 0 to 1, and that is equal to 1. Let's now consider the third path, that is from 011 to 111. In this case, the value of x changes from 0 to 1, value of y is equal to 1 and value of z is equal to 1. And dl in this case will be equal to dx times x hat. Therefore, integral v dot dl is equal to integral 0 to 1 x square dx, that is equal to x cube divided by 3 from 0 to 1, which is equal to 1 by 3. And the total of the line integral will be equal to 0 plus 1 plus 1 by 3, which is equal to 4 divided by 3. The third part of the problem is calculate the line integral from the origin to the point 1, 1, 1 in a straight line. So that is from 0, 0, 0 to 1, 1, 1. In this case, x is equal to y is equal to z, and these three values changes from 0 to 1. And in this case, integral v dot dl is equal to integral x square dx plus 2yz dy plus y square dz, and this is equal to integral 0 to 1 x square dx 2x square dy, since x, y and z are equal, plus x square dx. So this is equal to integral 0 to 1 4x square dx, which is equal to 4x cube divided by 3 from 0 to 1, that is equal to 4 divided by 3. Now the final part of the question is to calculate the line integral around the closed loop that goes out along path A and then back along path B. We already have calculated that the total value of the line integral in going along path A is equal to 4 by 3, and the total value of the line integral in going along path B is also again equal to 4 by 3. So since it is a return path, along path B will be equal to negative 4 by 3. So the total line integral will be equal to 4 divided by 3 minus 4 divided by 3, and that will be equal to 0. Surface integral. Surface integrals appear in the same form as line integrals and has the form integral s v dot dA. Here dA is an infinitesimal element of area, which is also a vector. The area element dA is often written as dA equal to n hat times dA, where n is a unit vector normal to the area element on the surface. It will always be taken in the positive direction. There are two conventions for choosing the positive direction. First, if the surface is a closed surface as that of a balloon, by convention the outward normal is taken to be positive. In this case, we'll put a circle in the integration line and represent the surface integral as integral s v dot dA. Second, if the surface is an open surface, the positive normal depends on the direction in which the perimeter of the open surface is traversed. If the right hand fingers are placed in the direction of travel around the perimeter, the positive normal is indicated by the thumb of the right hand. If vector v describes the flow of a fluid, that is mass per unit area per unit time, then integral v dot dA will represent the total mass per unit time passing through the surface. And this integral hence has an alternative name, the flux. Ordinarily, the value of a surface integral depends on the particular surface chosen. But there are special classes of vector functions for which it is independent of the surface and is determined entirely by the boundary line. We will now try to solve this problem. Calculate the surface integral of V over 5 sides excluding the bottom of the cubical box shown in the figure. Let upward and outward be positive direction as indicated by the arrows. So we have to calculate the total flux or the total outward flow by the cubical box shown in this figure. You can also see the direction of the positive unit vectors. Let us first consider the plane for which x equal to 2. In this case, the area element dA will be equal to dy times dz x hat. Therefore, v dot dA will be equal to 2xz dy dz. Therefore, integral v dA is equal to integral 2xz dy dz. This is again equal to 2 times 2z dy dz, that is 4 z dy dz. So this is equal to 4 times integral y varying from 0 to 2 dy times z varying from 0 to 2 z dz. So this is equal to 4 times y from 0 to 2 times z from 0 to 2, which will be equal to 16. Let's now consider the phase for which x is equal to 0. In this case, dA will be equal to dy dz times negative of x hat. So this is equal to negative of dy dz x hat. And v dot dA will be equal to negative of 2xz dy dz. This is equal to negative of 2 times 0 times z dy dz, which is equal to 0. Hence, the surface integral v dot dA is equal to 0. We will now consider the plane for which y is equal to 2. In this case, the area element dA will be equal to dx times dz y hat. Therefore, v dot dA will be equal to x plus 2 dx dz, and hence integral v dot dA is equal to integral x plus 2 dx dz, which is equal to integral 0 to 2 x plus 2 dx times integral 0 to 2 dz. This is equal to x square divided by 2 from 0 to 2 plus 2x from 0 to 2 times z from 0 to 2. This is equal to 4 by 2 plus 4 times 2, that is equal to 12. We will now calculate the surface integral for the surface for which y equal to 0. In this case, dA will be equal to negative of dx dz times y hat. Therefore, v dot dA is equal to negative of x plus 2 dx times dz. Hence, integral v dot dA is equal to integral negative of x plus 2 dx dz. So this is equal to negative of integral 0 to 2 x plus 2 dx times integral 0 to 2 dz. When we integrate this will turn out to be negative of 12. For the plane z equal to 2, dA is equal to dx dy times z hat, and v dot dA is equal to y times z square minus 3 dx dy. Since z is equal to 2, we have y times 4 minus 3 dx dy, which is equal to y times dx dy, and hence the surface integral becomes v dot dA is equal to integral 0 to 2 y dx dy. This is equal to integral dx from 0 to 2 times integral 0 to 2 y dy. This is equal to x from 0 to 2 plus y square divided by 2 from 0 to 2, and this is equal to 2 plus 4 by 2, that is equal to 4. Now the total flux will be integral s v dot dA, which is equal to 16 plus 0 plus 12 minus 12 plus 4, which is equal to 20. The volume integral. A volume integral is an expression of the form integral v t d tau, where t is a scalar function and d tau is an infinitesimal volume element. In Cartesian coordinates, d tau may be written as d tau equal to dx, dy and dz. For example, if T is the density of a substance, which might vary from point to point, then the volume integral would give the total mass. Occasionally, we shall encounter volume integrals of vector functions as integral v d tau equal to integral vx x hat plus vy y hat plus vz z hat times d tau, which is equal to x hat integral vx d tau plus y hat integral vy d tau plus z hat integral vz d tau. We have taken the unit vectors outside the integral because they are constants. Let's now calculate the volume integral of the scalar function t equal to x, y, z square over the prism as shown in the figure. We can write the volume integral as integral t d tau equal to integral x, y, z square dx, dy, dz. We can do the integral in any order. For this case, let's integrate the term containing x first, then y, and then finally z, so that the integral can be written as integral z square dz, then integral y dy then integral x dx. So we'll perform the integration in this order. We'll perform the integration with respect to x first, and then perform the integration with respect to y, and finally we'll perform the integration of the function with respect to z. To proceed further, we'll have to find the equation of the sloping surface. The equation of a plane with intercepts a0, 0, 0b0 and 0, 0, c is given by x by a plus y by b plus z by c equal to 1. For the plane that we see in this figure, there are only two intercepts at x equal to 1 and then y equal to 1. There is no z-intercept, and in this case, this equation modifies to be x divided by 1 plus y divided by 1 plus 0 equal to 1. From this, we write an equation for x as x equal to 1 minus 1. Now we know that x runs from 0 to 1 minus y. Therefore, the inner integral becomes 0 to 1 minus y x dx. This is equal to x square divided by 2 within limits 0 to 1 minus y, which is equal to 1 minus y the whole square divided by 2. Now the second integral is integral 1 minus y the whole square divided by 2 times y dy. The equation for the sloping surface that we have written was x plus y equal to 1, and in this case this becomes y equal to 1. Therefore, we conclude that the integration limit of y runs from 0 to 1. So this is equal to 1 by 2 times 1 minus 2y plus y square y dy 0 to 1, which is equal to 1 by 2 times integral 0 to 1 y minus 2 y square plus y cube times dy. This is equal to 1 by 2 times y square divided by 2 minus 2 y cube divided by 3 plus y raised to 4 divided by 4 from 0 to 1. This is equal to 1 by 2 times 1 by 2 minus 2 by 3 plus 1 by 4. This will be equal to 1 by 24. Now we shall perform the third integration, which is integral z square times 1 by 24 into dz. In this case, z runs from 0 to 3. Therefore, the integration limit is from 0 to 3, and this is equal to 1 by 24 times z cube divided by 3 from 0 to 3. This is equal to 1 by 24 times 3 raised to 3 divided by 3, that is equal to 9 divided by 24, which is equal to 3 divided by 8. We will try to solve this problem now. The problem is to calculate the volume integral of the function t equal to z square over the tetrahedron with corners at 0, 0, 0, 1, 0, 0, 0, 1, 0 and 0, 0, 1. The tetrahedron has been shown in this figure with the corresponding intercepts. Now, the volume integral is given by integral v t dot d tau is equal to integral z square dx, dy and dz. We can perform the integration in any order, and the simplest way will be to perform the integration of z at the very last, so that this equation can be written as equal to integral z square integral dy dz, and the inside integral is integral dx. We'll perform the integration with respect to x first, and then we'll perform the integration with respect to y, and finally we'll perform the integration with respect to z. Now we have to find the equation for the sloping surface. The equation of a plane with intercepts at a00, 0b0 and 0c, as we have seen earlier, is given by x divided by a plus y divided by b plus z divided by c is equal to 1. Since the intercepts are at 1, 1 and 1, we have the equation for the sloping surface as x plus y plus z equal to 1. From this equation we'll write x as equal to 1 minus y minus z, and the integration with respect to x runs from 0 to 1 minus y minus z dx, which is equal to 1 minus y minus z. For a given z, y ranges from 0 to 1 minus z. So the y integral is integral 0 to 1 minus z, 1 minus y minus z times dy. This is equal to y minus y square divided by 2 minus yz within the limits 0 to 1 minus z. This is equal to 1 minus z minus 1 minus z square divided by 2 minus 1 minus z times z. This is equal to 1 minus z times 1 minus z minus 1 minus z the whole square divided by 2. This is equal to 1 minus z the whole square minus 1 minus z the whole square divided by 2, which is equal to 1 minus z the whole square divided by 2. And finally, the z integral is integral 0 to 1 z square 1 minus z the whole square divided by 2 times dz. This is equal to 1 by 2 times integral 0 to 1 z square times 1 minus 2z plus z square times dz, which is equal to 1 by 2 times integral 0 to 1 z square minus 2 z cube plus z raised to 4 times dz, which is equal to 1 by 2 times z cube divided by 3 minus 2 z raised to 4 divided by 4 plus z raised to 5 divided by 5, and the integration limit is from 0 to 1. So this is equal to 1 by 2 times 30 multiplied by 1 by 3 minus 30 multiplied by 1 by 2 plus 30 multiplied by 1 by 5, the whole divided by 30, which is equal to 1 by 2 times 10 minus 15 plus 6 divided by 30, which is equal to 1 by 60.